Assalamualaikum warahmatullahi wabarakatuh. I am Ainon Atikah of the Jafri and I will present the chapter 1 of the assignment 2, which is the heat pump. First of all, the question is asking on the function of heat pump and function of its devices. Theoretically, the heat pump is an electrical device that transfer heat from one place to another place with the mechanical power. And as you know, there are 4 important devices or components in the process of heat pump. First of all is the compressor, then is evaporator, next is the expansion valve, and lastly is the condenser. All of these devices has its own function. For example, the compressor and also the expansion valve will convey the high pressure and the high temperature into the low pressure and the low temperature. And then the condenser and also the evaporator will extract heat from the system to the surrounding, from the surrounding and to the system to maintain the temperature. Moving to the next slide, we will learn on how heat pump works. There are a few phases of the heat pump operation. First of all, the process will begin when the refrigerant enter the evaporator coil in a liquid state and then transform its state to the gases and exits the evaporator coil. And it will pressurizes the gas mechanically. Next, the refrigerant will enter the compressor. The compressor will raises the temperature of refrigerant so that the refrigerant will exit the compressor. Then the refrigerant will be transferred into evaporator to maintain the temperature so that there will be more heated. There will be more heat that can be absorbed. The next question of the assignment 2 in the chapter 1 is to find the heat transfer. The heat transfer from the compressor is assumed as 0 since there is no kinetic energy and potential energy and it is negligible. And also that at the compressor is at the adiabatic state. After that, we determine the heat transfer from the condenser. And the heat transfer from the condenser that we had been obtained is negative 15.04 kilowatt. And this process is involve heat transfer from the refrigerant in the condenser to the air flowing through the condenser. And this heat transfer from the condenser does not require work and also no kinetic and potential energy, which is it is negligible. First step, we find the heat transfer of air by finding its mass flow rate, which is 0.499 kilogram per second, and then we substitute the mass flow rate into the formula of heat of air, and we got 15.04 kilowatt. And then we equal the heat of condenser is equal to negative of heat of air, so that the heat of condenser is equal to negative 15.0 kilowatt. Finally, we have obtained the heat transfer to the refrigerant in the evaporator. As you can see, we use the same principle as the compressor, which is first we find the Q air of the Q air in the evaporator, and then we get the mass flow rate of the air, which is 1.61 kilogram per second, and we equal the Q air equal to Q evaporator, and we get the final answer is negative 19.40 kilowatt. So that is all for chapter 1. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. My name is Muhammad Hadif Iqbal bin Radzi Cham, and now I will briefly explain regarding the Carnot heat pump. So basically, heat pumps, air conditioners and refrigerators utilize heat transfer from cold to hot. They are heat engines run backward. It says backward rather than reverse because except for Carnot engines, all heat engines, though they can be run backward, cannot truly be reversed. Heat transfer occurs from cold reservoir, which is QC, and into a hot one. This requires work input, which is W, which is also converted to heat transfer. Thus, the heat transfer to the hot reservoir is QH equal to QC plus W. A heat pump's mission is for heat transfer, which is QH, to occur into a warm environment, such as a home in the winter. The mission of air conditioners and refrigerators is for heat transfer, QC, to occur from a cool environment, such as chilling a room or keeping food at lower temperatures than the environment. Actually, a heat pump can be used both to heat and cool a space. It is essentially an air conditioner and a heating unit all in one. So in this section, it will concentrate on its heating mode. Heat pumps, air conditioners and refrigerators are heat engines operated backward. The diagram shown here is based on a Carnot reversible engine. For a schematic diagram showing that heat transfer from a cold reservoir to a warm reservoir with a heat pump, the direction of W, QH and QC are opposite of what they would be in a heat engine. And for B diagram, it is a reverse Carnot cycle following path A, D, C, B and A. The area inside the loop is negative, meaning there is a network input. There is heat transfer QC into the system from a cold reservoir along path D and C, and heat transfer QH out of the system into a hot reservoir along path B and A. The great advantage of using heat pump to keep home warm rather than just burning fuel is that a heat pump supplies QH equal to QC plus W. Heat transfer is from the outside air, even at a temperature below freezing, to the indoor space. One only pays for W, which is work input, and get an additional heat transfer of QC from the outside at no cost. In many cases, at least twice as much energy is transferred to the heated space as is used to run the heat pump. When fuel is burned to keep home warm, one has to pay for all of it. The disadvantage is that the work input required by the second law of thermodynamics is sometimes more expensive than simply burning fuel, especially if the work is done by electrical energy. So, from the question, given that heated space temperature is 25 degrees Celsius, the outdoor air temperature is 2 degrees Celsius, the heating load is 55,000 kilojoule per hour, and the heat pump power consumption is 4.8 kilowatt. For assumptions, the first one is steady state operation, and the second one is an average price of 11 cents per kilowatt hour for electricity. So, for the solution A, the coefficient of performance of this Carnot heat pump, we will get 12.96, and for the required work input to this heat pump is 101,880 kilojoule. So, the time the heat pump ran that day would be 21225 seconds, which is equivalent to 5 hours. For B, using the total heating cost, which is work input times price, the cost that we will get is $3.11. And for C, if the resistance heating would have been used, the entire heating load for that day would have will be met by electrical energy. After calculating the new heating cost using QH times price, the new cost would be $40.33. So that's all from me. Thank you.
Assalamualaikum warahmatullahi wabarakatuh. I am Zhafir Bin Zubir. So now we take a look on the understanding application of thermodynamic. What we're going to discuss here is how does a nozzle generate kinetic energy. Nozzle generate kinetic energy by accelerating the fluid. So how nozzle accelerate the fluid? It accelerates by going from higher pressure to lower pressure. Fluid get accelerated and due to which kinetic energy generated. Based on the Bernoulli's equation, now let pressure at high pressure point is P1 and velocity is V1, and for low pressure let P2 and velocity at this point is V2. We can assume inlet and outlet point are at the same level, so Z1 equal to Z2. So by applying Bernoulli's equation between point 1 and point 2, we can get as the Bernoulli's equation stated on the slides. P1 is greater than P2, so from equation 1, it can see that V2 should be greater than V1 to balance the equation. The higher the pressure pushes harder than the lower pressure, so there is a net force on any mass element to accelerate it. So it shows that from Bernoulli's equation that how nozzle generate kinetic energy by accelerating the fluid from higher pressure to low pressure. In terms of first law, the kinetic energy must be balanced by opposite change in another stored energy form. PV energy must decrease if kinetic energy increase. Next, we discuss on what is the difference between a nozzle, flow and throttle process. The nozzle generates kinetic energy by accelerating fluid from high pressure to low pressure. In throttling process, fluid also flows from high pressure to low pressure, but the pressure drop does not generate kinetic energy because in throttling process, pressure drop due to flow restriction and this represents a loss. In throttling process, a throttle valve is used to restrict the fluid flow. In the characteristic of throttling process here, no heat transfer and no work transfer is done by this process. It also no change in enthalpy from state 1 to state 2, which is H1 equal to H2. It also no change in enthalpy from state 1 to state 2, which called as isenthalpic. The process will be adiabatic, mean insulated. The process is irreversible because of some friction of the molecule to make it irreversible. A nozzle is a steady-state, steady flow device to create a high-velocity fluid stream at the expense of its pressure. It is controlled in an appropriate manner to expand the fluid to a lower pressure. Since the objective of the device is to increase the flow velocity, the kinetic energy term cannot be ignored. Usually, the process through the nozzle is treated as the adiabatic. Since there are no moving parts, shaft work is zero. The fact is, the first law is just a conservation of energy equation. Kinetic energy of the fluid at the inlet and outlet of the flow restriction can and should be taken into account as part of the first law equation. Taking the kinetic energy into account is never going to give you a wrong answer. Even when the flow is considered isenthalpic, then the difference in kinetic energy is small. It is only because the kinetic energy is small that we can often neglect it. Generally, the kinetic energy is small when the device of flow restriction is not made to accelerate the fluid flow and the flow velocity is not substantially increased. Things like valve and orifice do not have the geometry needed to efficiently accelerate the flow. This conversion of pressure to kinetic energy that determines if a restriction can be estimated as being isenthalpic or not. If look only at the pipe and nozzle, we might also add in kinetic energy trying to determine the local physical state of the fluid as it travels along the pipe. Next one is we discuss on what if the throttles a saturated liquid, what happened to the fluid state, and what happened if this is done to an ideal gas. So what if a throttle are saturated liquid. And what happens? The state from saturated liquid to a lower pressure with the same H give a two-phase state. So some of the liquid will vaporize and it become colder. So what happen if this done to an ideal gas? If this done to an ideal gas, we can observe that P in is greater than P out and V in is lesser than V out, where P is pressure and V is velocity. The observation confirmed the theory that H in equal to H out regarding to H equal to U plus PV, which is V equal to specific volume. So if pressure decreases, then specific volume must increase. If enthalpy is to remain constant, assuming U is constant, because of mass flow rate is constant, the change in specific volume is observed as an increase in gas velocity, and this is verified. So if the same process happen in an ideal gas, then same H give the same temperature. If the same process happen in an ideal gas, then same H give the same temperature at a lower pressure. Liquid may evaporate.
Assalamualaikum warahmatullahi wabarakatuh, and a very good day to everyone. My name is Umairah Binti Zakaria and I am from class of EH2202. So today I am going to explain a little bit more, continuing on the other half of chapter 3, understanding on applications of thermodynamics. So let's move on to the question number 4. And in this question, there are 3 things being asked in a question. So we're going to start off with the first part as highlighted in the slide. Now, to answer the question, so the power is actually generated from the water in the high reservoir, which they will travel through a pipe known as penstock. So from the diagram that I've included in the slide, you can see that there is an elevation created by the penstock. Also, the diameter of the penstock towards the turbine, as you can see, it's slightly reduced in number of diameters. So both the elevation and narrowing of the penstock towards the turbine actually aims to increase the fluid velocity, and hence it creates kinetic energy as the pressure decreases. So this high kinetic energy flow actually impacts a set of rotating blades which is attached to the turbine together with a shaft inside the generator. Hence the rotating action actually converts the mechanical energy created into electrical energy, and then it is supplied for domestic use. Now moving on to the second part of the question, which term in the energy equation are important if the control volume is the turbine only? Now, given in the slide is the steady flow energy equation, which involves various terms like Q, rate of heat transfer between control volume and its surroundings, W, which is the power, H2 minus H1, enthalpy change in the fluid, V2 squared minus V1 squared over 2, kinetic energy, and G times with Z2 minus Z1, which is the potential energy. Considering that the control volume is turbine only, it is assumed that W, which is the power term, is important in this case. For a turbine, W or power term, the term power referred as the shaft power. As turbines transmit a power through a shaft, which in a turbine it is normal to assume that Q, the kinetic energy, potential energy, are equals to 0. Same goes to enthalpy, as it is the same fluid assumed with no heat transfer involved in a hydroelectric power generator. Now, if the control volume is the turbine plus the upstream flow up to the top of the lake, which determine the energy equation, are then important. So to answer this question, in the question, it is actually an addition to the first condition, where now the upstream flow up to the top of the lake is an additional condition, where just now is this turbine only. So normally potential energy is always neglected, but in this case potential energy is important because it is significant, as it involves pumping a fluid from lower region to the high elevations, and in this case people would normally are interested to find the required pumping power. So in reality, actually, this thing do happen where water in the lower reservoir will be pumped up to the high reservoir. This is normally happen when there is a high demand of electricity, but high reservoir water are insufficient to produce electricity as a normal flow would do. Therefore, they will do the reverse, where the water from lower reservoir will be pumped up to the higher reservoir so that it could spin the turbine and generate electricity. And this is often referred as pumped storage hydroelectric power system. Now moving on to the next question, that is question 5. Also in this question there are two things being asked at once. So I would like to, of course, answer that separately. So we'll start off with the part 1. If you compress air, the temperature goes up. Now to answer this question, so basically the act of compressing by external force would cause the work to be done onto the system, and that causes the gas molecules that is being compressed to move faster, hence increasing the internal energy. So the rise of the internal energy will also cause the rise in temperature, as temperature and internal energy are directly proportional to each other. Now to answer the next question, that is when the hot air at high pressure flows in long pipes, it eventually cools to ambient temperature, and how does that change the flow? So to answer this question, high pressure of hot air causing the rise in temperature, but at one point as the temperature rises to an infinitesimal amount, or we can call it as based on my understanding, it's the capacity limit, the heat inside the gas will be transferred out to the link, hence causing a temperature drop to a certain value, making it constant at the value. Plus, if the flows are at constant pressure and cools, where there will be increase in density and volume decrease, slowing it down for a same mass flow rate m equals to rho AV and flow area. Now moving on to the last question. A mixing chamber has all flows at the same pressure, neglecting losses. A heat exchanger has separate flows exchanging energy, but they do not mix. Why have both kinds? So to answer this question, we'll start off with a mixing chamber. So mixing chamber is a steady flow engineering device. It is also known as open type thermodynamic. It is used to make two streams of fluid with different temperature for a temperature change that is somewhere between the two temperatures. So the temperature alteration is highly dependent on the mass flow of the two streams in comparison to each other. Hence, it is classified as direct heat exchanger. Based on mass principle, the sum of incoming flow should equals to sum of fluid leaving. So assuming that all QW, potential energy and kinetic energy, would equals to 0. As example, A normal shower that are fitted with T-elbow that acts as a mixing chamber for both hot and cold water streams that enable us to have the shower at a preferred warmness or coolness. In short, mixing chamber involve mixing of two or more streams with different temperature to exchange heat, and mixture are yielded as a product for use. Whereas it's a little bit different for heat exchanger. It is also a steady flow engineering device, but two moving fluid streams exchange without mixing. So to visualize that, heat exchangers normally consist of two concentric pipes with different diameters each. So one fluid will flow in the inner pipe, and the pipe will be enclosed with another pipe, where the space between the inner pipe and the other pipe, which is the outer pipe, will be filled with another fluid, and thus the temperature difference between the two fluids within different pipes will cause the heat exchange to occur from the hot fluid to cold fluid through the wall of the pipe. Heat transfer can increase by creating several turns inside that provide more heat transfer, thus increasing the rate of heat transfer as well. So, in a nutshell, heat exchanger functioned to allow heat exchange to occur without mixing or affecting the fluid involved in the process. So that's all from me. Thank you.
In conclusion, heat pump is an electrical device that extract and transfer heat from one place to another with the mechanical power. And heat pump is usually used in the cooling and heating system. In chapter 1, we have discussed the function of heat pump, the function of the heat pump component, which is the compressor, the evaporator, the condenser, and also the expansion valve. And then we also have calculate the heat transfer from the compressor, the heat transfer from the condenser, the heat transfer to the refrigerant in the evaporator. And in the evaporator and also in the condenser, the process involved of heat transfer from the refrigerant in evaporator or condenser to the air flowing of evaporator and the condenser. In chapter 2 of the assignment, we have learned the principle of the Carnot heat pump, which is the mechanical system that transfer heat from one place with the lower temperature to the another place with the higher temperature. And for example, the heat is transferred from the cool place to the warm place. Lastly, in chapter 3 of the assignment, we have summed up with several engineering devices such as nozzles, turbine, mixing chamber, and heat exchangers, which is all of these devices are classified as a steady flow devices, and it operate under a long period of time and in a constant condition. Therefore, problem based on the question was to aim and observe various terms in steady flow energy equation applied in these devices and how a certain condition might affect the term and its value. So, that is all from us.